The next concept that we are going to see is Chebyshev's theorem. Okay, when I was discussing about this mean and variance, I said that this x is the random variable to a maximum, mu is the average or expected value on this random experiment, and sigma is the standard deviation. So this Chebyshev theorem is going to deal with something of this probability. Okay, so we perform some random experiment. Okay, so this random variable is going to measure the output of this random experiment, and this mu denote the mean of this random variable. Okay, and sigma is the standard deviation. Okay, generally I told you that this is the general stuff. The probability of this quantity is always smaller than or equals 1. Okay, so this Chebyshev theorem is going to calculate the probability of such thing, but if you notice, this deviation is bigger than k sigma. Probability of this is going more than k sigma is smaller than or equals 1 upon k square. Okay, here if you let k to be equal to 1, then what is happening? Probability of x minus mu is greater than sigma is smaller than or equals 1. We know it is going to happen, right? So the total probability is always 1, but if you choose k is more than 1 something, okay, it is 2 sigma, it is 1 upon 4. Okay, so here the general stuff is with k sigma, with k positive is denoted, but it is better to take k bigger than 1. Okay, the consequence of this is probability of x minus mu less than k sigma is greater than or equals 1 minus 1 upon k square. Okay, so if you see, it is something which is, so it is covering some quantity and the probability is smaller than or equals 1 upon k square. So whatever is not covered in this is covered in the second statement. So since it is smaller than or equals, of course here it is greater than or equals, the remaining thing comes here. Okay, these two are the two different versions of Chebyshev's theorem. Mostly this first is the Chebyshev's theorem and the second is the consequence of it. Okay, here let me tell you the usage of this one. Okay, so as I was saying about some tube light and all. Okay, so this x is the lifetime of tube light. Okay, and mu is the average and sigma is the standard deviation. So you are expecting this x minus 1000 you are saying. Okay, and it is okay, sigma is some value, so it is greater than 2 sigma. This is what we are expecting. So to 2 sigma it is acceptable. Okay, so that is what the company says, but what is the probability that it is going more than 2 sigma? Okay, suppose if you evaluate it, what is going to, it is the set of all x such that x minus 1000 less than or equals 2 sigma complement, isn't it? So this is nothing but 2 sigma less than or minus 2 sigma less than or equals x minus 1000 less than or equals 2 sigma, which is nothing but 1000 minus 2 sigma less than or equals x less than or equals 1000 plus 2 sigma. Supposing, okay, the sigma is some 50 hours. Okay, or let us take it as 100. Okay, let it be 75 hours. So this would be what, 100 minus 2 times of 75 is 150. It is 850 less than or equals x less than or equals 1150. Okay, if the light is glowing between 850 to 1150, it is fine, but it is the complement. Okay, that is, this is the set okay, in which the light is glowing for no hours till 850 hours, and it is glowing more than 1150 hours to infinity. Is it acceptable? So if it is happening, if suppose the light is glowing less than 850 hours, the company will be in trouble, in the sense that consumers will come and lodge a complaint that you are saying that it will glow for 1000 hours but it is not glowing. The reputation of the company will go down. Whereas if it is glowing for more than 1150 hours, it means the lifetime of the tube light is more than what the company expects. It means the consumers will not come to buy the product again in the expected time. Okay, so it is working more than they expected. It means it is kind of a loss to the company. Okay, so we are calculating the probability that these two worst cases happen. Okay, this is a rough estimate of the probability, and I'm telling you this is not going to give you the better estimation, but still, to start with some estimation of the probability, this Chebyshev's theorem is useful. Now let us look at a problem. Here the random variable x denote the number obtained from a Faraday, which means what are the possible outcomes? It is 1 to 6, isn't it? And for each possible outcome, the probability is 1 upon 6. Okay, here we are asked to prove that this Chebyshev inequality gives this quantity, and compare. We'll have to compare this with the actual probability. Okay, so let us find out the mean. Mean is what? Expectation of x. Okay, when we calculate it, we are getting it to be 7 upon 2, that is 3.5. And expectation of x square comes out to be 91 by 6. So it is 91 by 6 minus 3.5 square is this 2.9167. It is what? It is sigma square. We will have to calculate sigma from this. Okay, so just take the square root of this 2.9167, which is your sigma. Now this is what the Chebyshev inequality tells us. Okay, now to evaluate what is this k, here we are asked to prove this quantity. So you just expect k sigma equals 0.25. You know the value of sigma, so you can very well calculate the value of k, which turns to be 1.46. Okay, and notice k is bigger than 1 now. Okay, so this gives us this quantity. So this 0.47 is 1 upon 1.46 square. Okay, so now let us calculate, compare this with the actual probability. We are asked to compare this with the actual probability, right? So mu is happening to be 0.35. So x minus 0.35 is greater than or equals 2.5. Okay, and which means what? Here again we will do this calculation. The set consisting of minus 2.5 less than x minus 3.5. Okay, uh, less than 2.5, the set the complement, that is the set consisting of, when we add this 3.5 to both the sides, we would get this happens to be 1 less than x less than, this would land in 6 complement, that is the interval 1 comma 6 complement. Okay, our x has to lie in this interval. So if you look at it, what we have is only this 1 and 6. 1 and 6 are not included in this interval. Okay, because we need greater than or equal to 2.5. Here greater than or equal to 2.5. So here we'll have to consider only less than 2.5. So this, so in this complement we have 1 and 6. Okay, so actually here they have consider only greater than, and that is why other stuff is coming. Just listen to what I say. So 1 and 6, probability of x taking the value 1 and 6, it is what? It is 2 upon 6, which is 1 upon 3, that is 0.33. Okay, the actual probability is 0.33, but our estimate is saying that it is smaller than or equals 0.47. So even here 0.14 variation is there. Our estimate is saying some quantity which is considerably larger than the actual quantity. And supposing if you take k to be equal to 2 here, okay, and when you perform these calculations, I am very sure that your this thing is here, your this thing is an empty set, the probability is 0, but Chebyshev inequality estimates it to be the probability is smaller than or equals 1 upon 2 square, which is 0.25, but actual probability is 0. Okay, here when you choose k to be larger and larger, this is the estimation is going worse and worse. Okay, thank you.